Welcome. This presentation introduces Unified Uncertainty-Aware Diffusion, U2Diff, our novel approach for multi-agent trajectory modeling. Our initial focus is on trajectory completion, where we generate multi-agent states. What sets our approach apart is the emphasis on uncertainty. We provide state-wise estimations using our denoiser, U2Diff. This powerful tool ingests noised trajectories and visible observations, and its output is twofold: the reconstructed states themselves, along with the measure of their uncertainty. In standard diffusion models, the denoiser is trained to predict the noise added during each forward diffusion step. Consequently, the commonly used simple loss directly minimizes the mean squared error between the predicted and true noise. Our approach goes a step further. We assume each predicted noise state follows a Gaussian distribution and introduce an additional loss term to explicitly model uncertainty. This is achieved by minimizing the negative log likelihood, NLL, of the predicted noise distribution for each agent state. This uncertainty-aware loss is used in conjunction with the simple diffusion loss, enabling the model to learn both accurate and consistent state-wise uncertainty. During the sampling process, the predicted noise is mapped to the state space using the denoising implicit formulation. This enables faster inference by skipping intermediate steps. Combined with an approximate variance propagation formula, this iterative process yields the final uncertainty estimates over the clean trajectory. Our analysis shows that starting variance propagation later in the denoising process, specifically at step 30 out of 50, consistently improves performance across all datasets. This delay helps avoid unreliable variance estimates that can occur early on, when the data has limited information. As shown in the plot, this adjustment leads to lower negative log likelihoods and more robust generalization. In the second part of our work, we present RankNN, a supervised approach designed to provide the error probability for each generated scene mode. For instance, in this example, we estimate that the third mode will have less error than the others. This predicted error, denoted as E, is forced to be positively correlated with the scene average displacement error by maximizing the Spearman correlation. The bottom figure, also included in our main paper, depicts examples from the 4 datasets used. Here, you can observe a clear correlation between error probability predicted by RankNN and the scene average displacement error, shown in blue. Next, we'll dive into the results visualizations for trajectory completion and forecasting across basketball, football, and soccer datasets. To qualitatively evaluate our model's uncertainty predictions, we will focus on 2 complementary visualizations based on 20 sampled modes under the same observations depicted in white. First, we select the best mode. This specific mode is defined as the one that minimizes the scene-level average displacement error. Crucially, for each state, U2Diff provides an explicit, quantitative uncertainty estimate. Second, we will display the mean and variance across the full distribution of 20 modes. These 2 visualizations offer a nuanced comparison. You'll see the predicted uncertainty of the best mode side by side with the uncertainty of the full distribution. This comparison will highlight the strong similarities between them, effectively showcasing the power of quantifying uncertainty explicitly using only the best mode.